Okay, welcome to the lecture on Bayesian statistics and Markov chain Monte Carlo methods. Um, we'll first briefly review Bayesian statistics. Um, in the following, we'll talk about Monte Carlo simulations to then extend those to Markov chain Monte Carlo methods. And finally, we're going to talk about metropolis coupled Markov chain Monte Carlo methods. And then we will discuss some phylogenetic proposals, and finally also briefly talk about reversible jump Markov chain Monte Carlo methods. Um, so as I've outlined before, in phylogenetics, Bayesian and maximum likelihood methods actually do have a lot in common. So what happens is that computationally, both approaches reevaluate the phylogenetic likelihood function over and over and over again for different tree topologies, branch length values, and model parameters. Um, so to just give you an idea, Bayesian maximum likelihood codes spend approximately 80 to 95% of their total runtime in those phylogenetic likelihood calculations on different trees and different parameters. So the key difference is that Bayesian methods sample the posterior probability distribution of the trees and all other parameters, while maximum likelihood methods strive to find like a point estimate, that one single maximum that maximizes the likelihood. Um, so talking about Bayesian phylogenetic methods, what they actually do is that they perform stochastic searches. That means that they do not really attempt to maximize the likelihood, but they try to integrate over it. So this is a key difference. Um, as a consequence of those stochastic or randomized searches, no numerical optimization methods for optimizing the model parameters and the branch lengths are needed, which makes implementation easier because implementing numerical optimization routines is difficult. Um, so basically, all parameters in a Bayesian phylogenetic inference are proposed at random. Um, so this is one advantage if you really want to implement such a method. Um, the other advantage I personally see is that it's substantially easier to infer trees under very complex statistical models of evolution using Bayesian statistics than it is using maximum likelihood. Okay, so to start, we will really have just kind of a short review of probabilities that we know that we're talking about. So we have this kind of table here with two characteristics, or the hair color and the eye color. So hair color can be brown or blonde, and then eye color can be light or dark. So basically we have like a sample here with those two properties. So just to remember, what is the joint probability if I take a random sample out of those 40 samples that I have here? So joint probability is a probability of observing both A and B. So for instance here, the probability of, if I take a random sample, of observing somebody with brown hair and light eye color is 5 over 40, so it's 0.125. That is the joint probability. Then something that is very important, especially in the Bayesian context, is the marginal probability. So here we say that we marginalize, for instance, over hair color, and this is an unconditional probability for a specific observation A. So for instance, the marginal probability of drawing somebody with dark eye color from our sample is the sum of the joint probabilities of observing somebody with dark eye color and brown hair plus the joint probability of observing somebody with dark eye color and blonde hair. And so this is, as you can see here, 20 over 40, so this is like 50%. So if I draw a random sample, and I asked the question like, what's the probability of drawing somebody with a dark eye color? It's 50%. Then finally we have the so-called conditional probability. So the probability of observing A given that B has occurred or that B is true. So the conditional probability of observing A conditional on B is the fraction of cases B in which B occurs where A also occurs with probability AB. So this is once again a joint probability. So for instance, the probability of observing somebody with blonde hair, given that he has light hair color, so the conditional probability of observing blonde hair color, conditional on or given that he's got light eye color, is the joint probability of observing blonde and light divided by the marginal probability of observing somebody with light eye color. And if you calculate that, this conditional probability is 0.75. Another important concept is the statistical independence. So two events are, just a second. So the statistical independence tells us that two events, A and B, are independent if their joint probability, so the probability of observing A and B, equals the product of their marginal probabilities, so the marginal probability of A multiplied with the marginal probability of B. So for instance, if we look at the joint probability of having light eye color and brown hair, so those are not independent of each other, so we see that it's not equal to the product of the marginal probabilities of having light eye color and brown hair. So this means in our example here that the events are not independent. Okay, so here is a summary again. The conditional probability of A given B is the joint probability of A and B divided by the marginal probability of B. The joint probability of observing A and B is the conditional probability of observing A given B multiplied with the marginal probability of B. And we can also write that the other way around. So the joint probability of A and B is the conditional probability of observing B conditional on A multiplied with the marginal probability of A. And so now coming to Bayes' theorem, if I can compute the conditional probability of A given B, how can I get the conditional probability of B given A? So that's how we come up with Bayes' theorem. So we just do a little bit of substitutions or some substitutions here. I guess this is probably very well known, so we just do the transformation, and now we have Bayes' theorem, right? So the probability of B, so the unobserved outcome, conditional on A, the observed outcome, so this is our, in our case, the observed outcome is the multiple sequence alignment, is just the conditional probability of A given B times the marginal probability of B divided by the marginal probability of A. Okay, and so we call those components, this one here is the posterior probability, this one here is the likelihood, then this one here, so the prior probability of the parameters we're interested in, the marginal probability of the parameters we're interested in, like the trees, the parameters, this is the prior probability distribution, and then finally the marginal probability is just the marginal probability, again in phylogenetics, of our alignment. Okay, So here, this has been extended for phylogenetics. So once again, what we want to compute is the posterior probability of the tree and all other relevant model parameters, so the tree topology, the branch lengths, the substitution rates, given the alignment. So this is the probability of observing the alignment given the tree and all other parameters. This is the likelihood, so we know how to compute that. Then we need to assume some sort of prior probability distribution for the tree and all other relevant parameters, and then we're dividing that through the marginal probability of the alignment. Okay, so here's a summary. The posterior probability is just like the distribution over all possible trees and model parameter values. The likelihood tells us how well the alignment fits the tree and the model parameters. And very importantly, the prior probability introduces prior knowledge and assumptions about the probability distribution of trees and model parameters, so the GTR rates, the alpha shape parameter, etc. So for instance, typically, if you consider just the tree topology parameter, we assume that all possible tree topologies are equally probable, so that's what we call a uniform prior. So we know how to compute this term. This is just the likelihood. This is something that we need to assume or give to our MCMC code, but then we still have the problem of the marginal probability. So how do we obtain that? So for the sake of simplicity, let's just assume here that our only model parameter is the tree topology itself, and marginalizing actually means summing over all unconditional probabilities. So the marginal probability of the alignment can be written as the conditional probability of the alignment given tree 0 plus the conditional probability of the alignment given t1, etc., etc., plus the conditional probability of the alignment, the joint probability, those are joint probabilities of the alignment and Tn. So basically this means that we really need to sum over the joint probabilities of the alignment and all possible tree topologies. So since the number of tree topologies grows super exponentially with the number of taxa in the tree, this then actually means that we cannot compute this marginal probability because it would just take too long. So we can then further rewrite this term. So the marginal probability of the alignment is the probability of the alignment given t0 times the prior probability of observing tree 0 plus the conditional probability of the alignment given t1 times the prior probability of observing tree t1, etc., etc. So this is basically just like the likelihoods of each tree multiplied with the prior probability. Okay. Now let's first have a look at this again, like at the general formula. So only taking the tree. So here we have the posterior probability, the likelihood, the prior probability, and our marginal probability, which, as I said before, in this very simple case where we just assume that the tree topology is the parameter, boils down to summing overall over the likelihoods for all possible tree topologies multiplied with the prior. So for instance here, a uniform prior would be 1 over n plus 1, so n plus 1 is just the number of possible trees, and this would then be a uniform prior, so you can kind of move that out of the summation and put it in front. So now we do have all the ingredients that we need for computing our posterior probability. However, computing the marginal probability of the alignment is actually prohibitive due to the large number of trees. And so another thing that you should note is that if we also have continuous parameters, because here we just have like a discrete parameter, so we're summing overall possible discrete values to get the marginal probability. If we had a continuous parameter, like for instance branch lengths or the alpha shape parameter of the gamma model of rate heterogeneity, this equation here for the marginal probability then actually becomes an integral because we're summing essentially overall possible values of a continuous parameter. Typically in terms of notations, if you read a paper, all parameters we integrate over, like the tree topology, the model parameters, etc., are lumped into a parameter vector that is denoted by the Greek letter theta. Okay, so here you can see the Bayes theorem in a more general form for this parameter vector theta, where we just put everything that we integrate over into. So once again, then we have like this probability density function f of theta conditional on A, which is still the alignment, and we call this a posterior distribution or posterior probability. We have our likelihood, our prior distribution or prior probability, and then we have the marginal likelihood here, which now actually, as I said before, in the general case becomes an integral if theta contains continuous parameters. And so this is sometimes called marginal likelihood, or also just normalization constant. Okay, so right now the only thing we know how to compute is the likelihood. So of the alignment given theta, all the parameters, so this is the likelihood of the tree. And then we have two problems. So problem number one is that the prior probability distribution needs to be given a priori, but how do we actually choose an appropriate distribution? Or what happens if we choose an inappropriate prior distribution that is not in any sense realistic based on the data we have? So this is at the same time the largest strength and weakness of Bayesian approaches, right? So the prior distribution allows you to inject prior knowledge to the inference process, but if you get that wrong, it may have it may actually impact the posterior probability distribution that you're trying to calculate. So this is both a strength and a weakness, because you can integrate prior knowledge, but you can also just get it wrong. And then of course, like, how then do we actually calculate the marginal? And so to explain this, we need to introduce some additional machinery, because we cannot really compute this analytically. Nonetheless, let us first have a look at the posterior probability distribution and what it looks like, how it is affected by various parameter choices. So this is the probability density function of theta of all parameters conditional on A, the alignment. So let's have a look at how this looks like in phylogenetics. Right, so what I already said is that this function f in the continuous case is called probability density function. Maybe just like a small reminder of what a probability density function actually looks like. So here we have our parameter x, and then on the y-axis we have our probability density function. And so the actual probability for that this parameter x falls between like 0.2 and 0.3 in this example is the area over the integral over the probability density function. So if I ask the question, how probable is it that x falls in the range between 0.2 and 0.3, I actually need to calculate the integral over the probability density function. So here are some properties. So the probability density function needs to be larger than 0 for all allowed values of x, right? So if you imagine that this is a branch length in a phylogenetic tree, you may not allow that it is negative. The total area under under the probability function fx evidently needs to be 1.0. So if I integrate from the smallest allowed value to the largest allowed value for x, this needs to be 1. And as I said before, so the probability that x, our parameter x, falls into an interval like 0.2 to 0.3 in our example is given by the integral of the probability density function over the specific interval. Okay, so here's a little example now how Bayesian phylogenetic inference works in phylogenetics. So here we have those 3 alternative unrooted tree topologies for the great apes, and here is how it works. So initially we know that there are like 3 distinct instances of this tree topology parameter, and now we have our prior distribution. As I said before, a priori we assume that all possible tree topologies are equally likely. Then we add some data or like observations to our model, to our Bayesian inference machinery. In this case, those are sequences, and we somehow get like a corrected distribution for those trees, like corrected by the data, and this is the posterior distribution. So here you would see that then maybe like tree number 1 here and tree number 3 here have a low posterior probability, and the tree that we actually prefer with a high posterior probability is this one here. Okay, and so like in this case we're dealing with discrete parameters, so our parameter space just contains like the 3 distinct tree topologies. Evidently here it would also be very straightforward to compute the marginal probability. Okay, so this is what I basically just said here. Okay, now the question is like, what happens to the posterior probability if we don't have enough data? So just consider like the stupid case where we have an alignment that just consists of a single alignment side. So what would happen to the posterior probability distribution in this case here if we don't have enough data? And well, the answer is that probably we'll just get the prior back, right? Because we don't have enough data to correct this distribution to get a good posterior probability distribution by the likelihood. Okay, so here's another example. Now we may want to include an additional model parameter or additional model parameters such as branch lengths, the rates of our nucleotide substitution models, and the alpha shape parameter of the gamma distribution into the model. So now our parameter vector would look something like that. So theta would contain the tree, this alpha parameter, all branch lengths, and all GTR rates. So now the posterior probability distribution would look something like that. So this is our probability density function of theta conditional on the alignment. And here, so this would be just like on the x-axis we have the parameter space of theta, and now here we would have some sort of distribution, continuous distribution like that. So tree 1, tree 2, and then tree 3. And now a very important property of Bayesian inference is that we can look at this distribution for any parameter of interest by marginalizing or integrating out all other parameters. So on this slide here, or this graph here, we focused on the tree topology. And once again, we obtain the probability for the different tree topologies by just integrating over this interval here, or basically just like summing over the posterior probabilities for the samples that we've drawn that contain tree topology number 2. So here is an example of how marginalization works. For the sake of simplicity, we're going to assume that we're only considering like 3 discrete values of the alpha shape parameter, right? So 0.5, which is high rate heterogeneity, 1.0, which is medium rate heterogeneity, and 5.0, which means low rate heterogeneity. And then in this table here, we have like the joint probabilities of observing alpha together with tree topology 1, this specific alpha value, alpha 1 with tree topology 2, and alpha 1 with tree topology 3, etc. So if we're marginalizing out, I said integrating out, but here we just have taken a couple of samples. So basically what we do is just that we either sum over the entries in the columns or we sum over the entries in the rows. So if we sum over the entries in the columns, we just get like the marginal probabilities of the different tree topologies. And then if we sum over the entries in the rows, so we marginalize out the trees, we get the marginal probabilities for the alpha values. Okay, right. So here's another example. So we can look at this distribution, at the distribution for any parameter of interest by marginalizing or integrating out all other parameters. So now here we focus on the three, discrete alpha values that we've picked, and this is our probability density function here, or the posterior probability, and this is the marginal probability distribution of A here, right? So we get 29% for A being 0.5, 33% for A being 1.0, and 38% for A equals 5.0. Okay, so key question is like, what is the main difference, or let's get back to the question what the main difference between Bayesian inference and maximum likelihood based inference is. And so maximum likelihood means that we're doing like a joint estimation of everything, and Bayesian means that we're doing a marginal estimation of everything. So if you just consider like the likelihood score being the value on the y-axis here, and on the x-axis we just have like some sort of parameter of interest, x, which could again be the alpha parameter. And so here you will see that maximum likelihood will actually prefer give you a tree that has the highest likelihood, so just like the highest point estimate here, or the highest peak, whereas Bayesian inference will actually prefer, so let's maybe start over again. So this is a parameter of interest alpha, right? And we have two alternative trees, tree A and tree B. So maximum likelihood will just give you, prefer tree A, or return tree A, if this is the tree that for some value of x gets like the absolute best maximum likelihood value. However, Bayesian inference will favor a tree B, which maybe doesn't have like this highest peak likelihood here, but that has like a higher likelihood value for a larger range of values of x, right? So here you say, okay, x is just a parameter value, as I said before, the alpha shape parameter of the gamma model of rate heterogeneity. And so this shows you how Bayesian inference and maximum likelihood inference, how they would choose among two distinct tree topologies. Okay, so now we've discussed a little bit about this, but we still really don't know how to compute this marginal likelihood. And so first we'll start with Monte Carlo simulation and integration. So that's kind of my personal way of writing down the Bayesian formula. So the posterior probability for theta, all our parameters conditional on the alignment, is just the likelihood times the prior divided by ouch, right? So ouch, because this is very painful and difficult to calculate. Again, we know how to compute the likelihood, so this is just the likelihood of the tree. We need to be careful when we choose the prior probability distribution for all parameters in our parameter vector theta. And then, well, problem number 2 is how can we calculate, or how can we actually approximate the marginal here. And so to explain this, we need to introduce some additional machinery to design methods for numerical integration, right? So we cannot compute this exactly, we know that, because there are just too many parameters. and too many values those parameters can take. So we need to come up with some sort of machinery for what we call numerical integration. Right. So here's one question. This is the x-axis. We have the parameter space of theta, and here we have on the y-axis we have the probability density or posterior probability. Right. So here's like a classic example of how Monte Carlo methods work. Like if I cannot calculate something exactly, I need to approximate it numerically. And so here what we do to actually calculate the famous geometric constant p using a Monte Carlo method, that's what we do. So we randomly throw points onto this rectangle here that contains a quarter circle for a certain number of times, n times. And then we basically just count how many points fall into the circle and how many points that we've thrown at this rectangle fall out of the circle. And then we just determine p as the ratio, like the fraction of overall points we've thrown divided by the number of points that have fallen into the circle. And so evidently this yields an approximation of the ratio of the two areas, so the blue area, the overall area and the red area, so the square and the circle. And quite evidently, the more, and you can see it here in the animation, the more points you throw at this rectangle, so the higher the n, the more samples you draw essentially, the closer you get to the correct value of p. Right. And so, talking about Monte Carlo integration, this is a method for numerical integration of calculation of m-dimensional integrals over R, so the real numbers. So essentially you approximate this integral that you cannot compute because it's too complicated just by 1 over n times the sum of the points you have computed. And so this theta is from the domain r to the power of m, like a large vector space in the real numbers. Keep in mind here that in Bayesian phylogenetic inference, this is actually not true because we also have this tree parameter, this weird discrete parameter. Right. And so I'll spare you this, but some key issues with Monte Carlo simulations is that while they draw those samples theta I of our function, of our probability density function f, completely at random, right? So they put like a completely random grid onto the posterior probability space that we're actually trying to approximate. And so one other key question is, well, how many points do we actually need to sample to obtain a good approximation? So that's kind of an open question. And finally, this domain, the real numbers, some vector of real numbers with m entries, might just be too large for random sampling, right? So what we would actually need is some sort of more intelligent sampling of this large parameter space. So random sampling will not really help us here. All right, so, and now this is what takes us over to Markov chain Monte Carlo methods that do exactly that. So they do like a more targeted sampling than Monte Carlo methods that just do like a complete random sampling. So the question here is, well, you know, we have our parameter space theta on the x-axis, and what we want to approximate is the posterior probability distribution of all our parameters in theta given the alignment. So what Monte Carlo methods do in very abstract terms is that they randomly sample points in this huge parameter space to approximate the interval. However, if you think about the posterior probability, well, in which parts of the distribution are we actually interested? We're really interested in the parts of the distribution that have high posterior probability values and not that much into the parts of the distribution that have like low posterior probability values. So what we want to do, what we want to achieve here with Markov chain Monte Carlo methods is that we want to sample um, more and more detail the areas of high posterior probability. So the question is like, how can we get like a good sample of those areas of high posterior probability more quickly? Um, and that's basically just what Markov chain Monte Carlo methods do. So they're designed in such a way that that we take more samples um, from the areas of high posterior probability, and like a nice property of the method is that the number of samples uh, taken in an area of high posterior probability is actually proportional to the posterior probability. So for instance, if I sample many trees here, I must sample many trees here and many tree topologies here, and I will not sample a lot of tree topologies from this area, like from this valley here. But we'll see that in more detail. Okay, so what Markov chain Monte Carlo methods are is that they are some sort of biased random walks. So the probability to evaluate or find a sample in an area of high posterior probability is proportional to the posterior distribution, right? So the higher the posterior probability distribution is, like the higher the value is, the higher the posterior probability is, the more samples I will take from here than from down here. Okay, so the main idea of Markov chain Monte Carlo methods is to use the grid or the samples into regions of high probability. And the way we do that is that we construct a Markov chain that generates samples such that more time is spent, so more samples are evaluated or drawn in the most interesting regions of the state space. So here, this Markov chain is completely unconnected to the Markov chain model that we use for nucleotide evolution, right? So this is actually the Markov chain that we use for nucleotide evolution is part of the model, whereas the Markov chain that we use here is part of the procedure of the numerical integration procedure. So this is very important to distinguish here. Of course, like the properties, the general properties of Markov chain still hold. Just as a side note, Markov chain Monte Carlo methods can also be used for difficult optimization problems from computer science, like the knapsack problem, for instance. And also note that MCMC, in terms of like the way the search procedure or the sampling procedure works, is somewhat similar to simulated annealing, but I'm not really going to cover that here. Okay, so now let's start explaining how MCMC works using the famous robot metaphor that was introduced by Paul Lewis for teaching MCMC methods. So the idea here is that, so this is the island of Crete that you can see has like a lot of mountains. Here's kind of a local maximum, and this peak up here is actually the absolute maximum, so the highest peak of Crete. And so the idea, what you do here with the robot metaphor, the idea is that you just drop a robot on this island and have it move around so it can measure its altitude. And what your actual goal is that you want to have this robot construct a topographical map for you of the island just by moving around and measuring its current altitude. So we drop a robot onto an unknown planet or island to explore its landscape. And so here's how it works. So this is the elevation. Of course, in MCMC terms, this is the posterior probability distribution, but now it's just the elevation. Right, so our robot randomly chooses to move right or left in this two-dimensional landscape. And so it moves a step to the right and it measures its altitude, so it will see that it's higher. So if it does an uphill step, it knows that it did an uphill step after moving to the right, it will always accept it, so it will always remain in this position. Now if our robot is here and chooses to move left, it makes a small downhill step, and this is usually being accepted because it will still remain in this kind of interesting peak area here of the mountain. Now if we have like a very steep slope here, so the robot is here and decides to go to the right, it will make like a huge downhill step, and those huge downhill steps are almost never accepted. But sometimes of course they must be accepted because there could be like a higher peak up here, right? So if we go back to our nice picture, assume our robot is here and makes a downhill step here. Well, in most cases it would go back to the peak area here, but of course it needs to traverse this valley to at some point actually find the highest peak of the island. Okay. Right, and now here comes maybe the most important point. So how do we actually decide whether to accept or reject a proposal? So the decision to accept or reject a proposal to go from a point 1 to point 2 is based on the ratio R of the posterior densities, or in our example just the elevations, of the 2 points and samples. Right, and so if we write this ratio down, this is the posterior probability of being at point 2 given the data. This is the posterior probability of being at point 1 given the data. And then we just expand this, so the prior and the likelihood divided by the marginal, and then of course over the prior of point 1 and the likelihood of point 1 divided by the marginal of the data. And we see that this actually boils down to just taking the ratio of the prior probability of point 2 multiplied with the likelihood of point 2 divided by the prior probability of point 1 multiplied with the likelihood of point 1. And this is really super exciting because we see here, like if we calculate this acceptance ratio like that, the marginal probability of the data actually cancels out. And so this means that we don't need to compute it. So this is really super important and very exciting because we can see that with this sampling procedure that we've designed, we do not need to compute this very complicated and complex marginal probability. Right. And so typically this is just written in a different way. So this kind of acceptance rejection ratio is typically just written as a ratio of the priors at the 2 points times the ratio of the likelihoods at the 2 points. So it's a prior ratio times the likelihood ratio. And just as a side note, so if we have a uniform prior, so if the prior probability of being at point 1 is equal to the prior probability of point 2, then this is just 1. So if I only have uniform priors, then basically our ratio is just the ratio of the 2 likelihoods, or in our case, in the example, the ratio of the 2 elevations. Okay, so here's an example. So at 1 meter, at an elevation of 1 meter, we move slightly to the right and measure the elevation, and we see now that we're at 2 meters, so the ratio is 2 over 1 and is larger than 1.0, so we accept automatically. If we're at 10 meters and we moved left, which took us down to 9 meters, the ratio is 9 over 10, so this is 0.9, and this actually means that we're going to accept the new position with a probability of 90%. Now if we're at 8 meters and go down to 1 meter, the ratio, the elevation ratio, is 1 over 8, so 0.125. This means that we will accept this new position with a probability of 12.5%. Okay. So this is basically how this acceptance rejection works. If the ratio is larger than 1, we always accept it, so because we're going uphill. If the ratio is slightly smaller than 1, well, we are going to accept it in most cases. If the ratio is much smaller than 1 or close to 0, then we're going to reject this move in most cases. Okay, right, and now we need to talk a little bit more about different distributions. So what we call the target distribution, that is will be shown in blue in the following slides. This is actually the posterior distribution we're trying to sample or approximate. Um, the proposal distribution is actually part of the MCMC machinery, so it decides at which point, like how far, how close from the current point in the landscape, we're actually randomly going to go next. So, and the choice of the proposal distribution has an effect of the efficiency of the MCMC algorithm. That means how fast it will get to those interesting areas of high posterior probability that we want to sample, and how long it's going to stay there. So what's shown in blue here is our target distribution, so our landscape, our posterior probability landscape. And now what is shown in red here is the proposal distribution. So that's part like of the program that the robot is actually executing. And so this one tells us like how far are we going to go left or right at random, right? So basically what you do here is that you're given this proposal distribution, the robot is given this proposal distribution, and then it just randomly draws from this distribution here to decide where to go next, right? So most of the time it will make rather small moves, but sometimes it may also make larger moves at the outer parts of the proposal distribution here. Okay. So, well, if we have a proposal distribution with a smaller variance, right, so like a more narrow proposal distribution, the advantage is that, well, it will rarely refuse to take a step because we're kind of staying more or less in the same area. But the disadvantage is that it will make smaller steps, so we will need more steps. More steps will be required to explore the entire landscape because, remember, like there could be a higher peak further here to the right. So now if we choose a proposal distribution with a larger variance, what happens here? Well, it can cover a large area quickly, but a lot of steps, like a lot of downhill steps here, if we have like this kind of flat distribution here, a lot of steps that the robot does will actually be rejected, right? So the robot may go here quite frequently and see that it's kind of at a substantially lower elevation and then go back to its initial position. So that's what rejecting a move means, that the robot tries to go to a new position here, evaluates the ratio of the elevations and sees that it's, in most cases, will then go back here to its original position and then try to do a next move. Okay. And so a proposal distribution that balances the advantages and disadvantages that we've discussed before yields what we call good mixing of the Markov chain. So talking about mixing, what this means is that a well-designed chain, Markov chain, or well-programmed robot, so to say, will just require a few steps until reaching convergence. That is approximating the underlying probability density function well enough from a random starting point, right? So it will just need a few steps to get like a good approximation of the probability density function. So the term is like somewhat fuzzy because it refers to the proportion of accepted proposals, so what we call acceptance ratio, generated by a proposal mechanism, right? So for instance, if the robot is programmed in such a way that it accepts like 60% of the moves, then it will have an acceptance ratio of 60%. And so here you should know that while this proposal ratio, or the acceptance ratio, should be neither too low nor too high, and typically we're targeting, if we want to design a good proposal mechanism, we're targeting something like 25%. And so this is the real art in designing Markov chain Monte Carlo methods. So what you do most of the time is that you're building and tuning, that you're trying to build and tune good proposal mechanisms. So this means that you have to select appropriate proposal distributions in such a way that they quickly approximate the distributions we want to sample. And of course, unlike in our very simple robot metaphor, where we just kind of, move to the right or to the left, the number of possible moves, like the ways you have to design possible moves, you have many more choices, and we're going to see that later on. So there's typically not only one type of move that you can do. Okay, so now we need to look again at the properties of the proposal distribution. So if this proposal distribution, as is the case here, is symmetric, then we actually use what we call the metropolis algorithm. So this is the simple case. So if the proposal distribution is symmetric, we have the same probability of moving like 1 meter to the right than as we have to move 1 meter to the left. That's no problem. And let me now outline the metropolis algorithm a little bit more formally. So this was introduced in 1953. How do we initialize our algorithm? Where do we start from? So as I said before, we just randomly drop our robot on the island we want to sample. So basically what you do is that you choose an arbitrary point, arbitrary values for all your parameters in theta. So an arbitrary starting point, theta 0 as first sample. And then you choose an arbitrary probability density. So this is our proposal distribution that gives you a transition from theta I to theta I plus 1 to the next step, and suggests a candidate for the next sample, theta I plus 1, given the previous sample, theta I, right? And so this probability density function is basically just your proposal distribution, right? It's got nothing to do with the posterior probability distribution that we're actually trying to approximate. And so for the metropolis algorithm, as I said before, this transition function Q, the proposal distribution Q, must be symmetric. So it must satisfy that the probability of going from theta I plus 1 to theta I is the same as going from theta I to theta I plus 1. So now how does that work? So we have our starting point, we have our proposal distribution, and now if we're at generation or iteration I, we generate a candidate theta star for the next sample by picking from the distribution theta I to theta star. And then we calculate the acceptance ratio. So this is the prior probability of theta star multiplied with the likelihood of theta star over the prior probability of theta I multiplied with the likelihood of theta I. So if the ratio is larger than 1, then theta star is more likely than theta I, which means that we automatically accept the candidate by setting theta I plus 1 to theta star. So this is like our next sample. Otherwise, as we've seen before, so if the ratio is below 1, we accept the candidate theta star with probability R. And so if the candidate is rejected, then theta I plus 1 is just like the previous sample, theta I. Right. And so just as a side note, this transition matrix here, this Q is just the same Q mathematically as we saw for substitution models and in the Markov chain lecture. Okay. So let's now have a look at how this works for phylogenetics. So in phylogenetics, while the initialization is that we choose a random tree with random branch lengths as a first sample. So if we just have like in our parameter vector theta, if we just have the tree topology and the branch lengths, we're considering this kind of simple case. So for each iteration I, we either propose a new tree topology or a new branch length and recalculate the likelihood. And then we calculate the acceptance ratio of the proposal of the proposed new tree or new branch length, and we accept the new tree or branch length or reject it. So what we also do is that we print the current tree at the current generation with its branch lengths to file every, let's say, k, for instance, 1,000 iterations, to actually generate a sample from the chain, right? So this is then the output of our MCMC method. We do that to avoid writing terabytes of files, so this kind of thinning, um, so meaning that we're just printing out samples every 1000 generations, and also because of the moves that will be done, the changes to the tree topology and branch lengths within 1000 steps will not be that large. So this technique is also known as thinning. Then in the end, after we've run the Markov chain long enough, and we'll get to this, we summarize the samples just using standard statistics like means, histograms, credible intervals, consensus trees, etc., etc. Right, and so now let's go back to our proposal distribution. So if we have like a robot in 3D, so those are lines of equal altitude. If we run our robot in 3D, here's what happens, why we are not really sampling the peak area. So here, in this example, our MCMC proposed moves to the right 80% of the time without the Hastings correction for acceptance probability, right? So now we get to the Hastings correction. If I have an asymmetric proposal distribution, like that will yield some sort of drunk robot that does not correctly sample my posterior probability distribution, I need to do something more for it to run correctly. So here if I have a proposal distribution that for some reason moves to the right in 66% of the cases and to the left in 33% of the cases, we somehow need to decrease the chances to move to the right by 0.5 and increase the chances to move to the left by a factor of 2 to compensate for this asymmetry and to get like a proper approximation of our posterior probability distribution. And so this is known as the Hastings correction and is introduced in our ratio calculation. So we have like the ratio of the priors for the 2 points, we have the likelihood ratio, and then we have the so-called Hastings ratio. So if Q is symmetric, if our proposal distribution is symmetric, then the Hastings ratio is 1, and we obtain the normal metropolis algorithm. If it's not symmetric, well, we get another factor here by which we need to multiply. And so more formally, using probability density function notation, so here our acceptance ratio R is a prior ratio, the likelihood ratio, and the Hastings ratio for the new proposed point theta star and the current point or the current sample theta I. Right. One thing to keep in mind is that, well, getting the Hastings correction correct is actually not trivial. So for instance, for many years, like from the beginning of Bayesian phylogenetic inference that started around the mid-90s until 2005, there was actually a bug in the Hastings correction for one of the very important moves, the so-called local proposal or local move that was used in Bayesian phylogenetics up to this point. So this move was, I almost got it right, introduced in 1999, and the incorrect Hastings correction was used until 2005. So this is a very nice paper, and the author states, so as part of another study, we estimated the marginal likelihoods of trees using different proposal algorithms and discovered repeatable discrepancies that implied that the published Hastings ratio for a proposal mechanism used in many Bayesian phylogenetic analysis is actually incorrect. Okay, so now let's go back to phylogenetics and see how we actually can use the output of Bayesian phylogenetic inference. So here, those are the samples that have been printed out, so the tree samples that have been printed out by our MCMC procedure. And so here, we may want to ask, like, what's the posterior probability of observing bipartition AB, CD, so that AB are together in the tree and separated from the remaining taxa. So how do we compute the posterior probability given this sample from our Markov chain? Well, this is very easy. So we just count from the sample generated by MCMC, and you can see here that, well, AB occurs in one, two, three trees. So this means like it occurs in 3 out of 5 trees. So the posterior probability of bipartition ABCDE is 3 over 5, which is 0.6. And so this approximates the true proportion, like the true posterior probability of bipartition ABCDE, if we have run the chain long enough and if it has converged. And this takes us like to the next problem. So if, for instance, we consider the frequency of this bipartition we're interested in and plot it over the number of generations, so the number of samples that our Markov chain has generated. So here, this is our random starting point. So we have like a period that it takes, period of time or generations, that it takes our MCMC chain to move to areas of high posterior probability. And then if we kind of continue monitoring the frequency of occurrence of ABCDE of this bipartition, at some point we'll see that this kind of stabilizes over generations, right? So it may stabilize at 0.6 as we've seen before. So this takes us to the problem of convergence. So how many samples do we actually need to draw to obtain an accurate approximation, right? So for how long does our robot have to stay on our island such that we have like a sufficiently accurate topographical map of the island? When can we actually stop drawing samples or tell our robot to stop moving around the island? So there are some methods for convergence diagnoses that essentially boil down to looking at graphs like this and doing some statistics like determining the variance of this frequency of the bipartition we're interested in. But we can actually never say that a Markov chain, metropolis coupled Markov chain, has converged. So the only thing that we can do is that we can diagnose using those methods for convergence diagnosis that it has not converged. So there exists like a plethora of tools for convergence diagnostics for phylogenetic MCMC. But what you should really keep in mind is that you never ever can say that whatever Markov chain, metropolis coupled Markov chain you've run has converged. So it is guaranteed by design of the method that if you run it to infinity, it will give you the exact value of the posterior probability landscape. But since we cannot wait for that long, we have to stop the chain at some point. So, for instance, if you consider a similar example, so just assume that this is the likelihood score of the trees that we're sampling, and this one on the top here is the entire landscape. But of course you don't have a view of the entire posterior probability landscape. You just zoom in here, and this was the burn-in, so the random starting point, and then at some point here, because this peak area is very flat, you have reached an area of apparent convergence, right? And so this here is an area of apparent convergence. You may say, well, I think just by looking at it, my Markov chain has converged, and thereby you may be tempted to just stop the analysis. Okay, so here's one solution for better handling those local peaks or local optima. What you can do here is that you just use several robots, or you just execute multiple chains that start from different starting points to explore your landscape, right? Instead of throwing one robot. So what we can do is that we just drop multiple robots on our planet or on our island whose topography we want to explore, and hope that those robots, just by random chance, one of the robots reaches the areas of higher posterior probability. But we can do that in a more intelligent way, and so this takes us over to metropolis coupled Markov chain Monte Carlo methods, which I'm going to explain in the following. So here, what we have is that we have robots that behave differently. And those are typically called heated versus cold robots, or heated versus cold chains. So we have one robot here, like the blue one, which is the cold one, that sees the landscape as is. But the hot robot, through some transformations that we do, sees like a flattened out version of that same landscape. And so this means that it can, because it sees this flatter version of the landscape, that it can more easily move around between peaks. So one important thing to know is that only, because this is the true landscape that we're trying to approximate or explore, only the cold robot, the blue one here, the cool guy, actually takes samples, right? Because those are the samples from the correct landscape here, whereas this guy here, like the heated robot, the nervous guy that's moving around back and forth, does not emit or take any samples, because he sees like a different version of that landscape. So let's see how that works. So this is metropolis coupled Markov chain Monte Carlo, MCMC. And what we do is that we run several chains simultaneously. We have one cold chain, the one that takes the samples, and typically several heated chains. And so those heated chains or heated robots explore the parameter space in larger steps, just because they see a flatter version of it. So to flatten the landscape, what we actually do is that the acceptance ratio R is modified as follows. So we calculate R as R over to the power of 1 over 1 plus H, where H is the so-called temperature. So evidently for the cold chain, we set the temperature to 0. And well, how we set the temperature for the hot chains is a bit of voodoo, right? So it's a lot of experimentation to see how that works. But what do we actually do with those heated robots? So every once in a while, the cold robot, the currently cold robot, so the blue one, exchanges information with the red robot. So it asks the red guy, hey, where are you? And then it actually evaluates the posterior probability for the correct version of the landscape. And we'll see that, well, the robot number 2 is now in a higher area of posterior probability. And what happens is that, well, they just swap states in that case, right? So if the formerly hot robot is in an area of higher posterior probability, now this one here becomes the cold chain, the cold robot, and then sees like the unflattened version of the landscape. And then the other guy here starts seeing like a flatter version of the landscape. So basically, the cold robot and the heated robots, just occasionally, every once in a while, every let's say 1,000 generations, communicate with each other. And if one of the hot robots is in a higher area of posterior probability, it then assumes the role of being the cold robot, etc. So I've presented this here in very simple terms, so the decision on when to actually swap is a little bit more complicated, but I will spare you the details. Okay, and as I said before, so here I should have actually changed the diagram a little bit. So here, robot number 1, the hot one, sees a flatter version of the landscape, and the cold robot sees actually the correct version of the landscape, this one here. As I said before, only the cold robot actually emits states or writes samples to file. You may remember those trees we looked at where we were interested in the frequency of occurrence of bipartition ABCDE. So it's only this cold robot that actually writes trees and other parameters to file. Okay, so now maybe it's a good time to have a few words about priors. So as I said before, the prior probabilities convey the scientist's beliefs about the data before actually having seen it. So one thing we can do if we don't really know what the prior probability of a parameter is that we use so-called uninformative priors, like the uniform priors that we've seen for the trees, where we say that every tree topology is equally likely a priori. And those uniform priors are also often called flat priors, right? Because there's like just a flat curve. Um, and so the differences that we then observe between the prior and the posterior distribution are attributable to the likelihood differences, which is like the other ingredient of our posterior probability ratio calculations. And evidently, priors, if you choose a prior incorrectly, they can bias an analysis. For instance, we could do something very stupid and choose an arbitrary prior distribution for branch lengths and say that they must be in the range 1.0 to 20. And so typically branch lengths in phylogenetic analyses for most data sets are much shorter. And so the question is, what happens if branch lengths are much shorter, right? So this actually shows you how you can easily bias an MCMC inference by choosing incorrect priors, so you will basically just get trees that have far too long branch lengths. Okay, so now I actually wanted to provide you some examples for phylogenetic tree proposals. So how does our robot that tries to find trees with high posterior probability work in practice? Right, so I will first talk a little bit about branch length proposals. So there are two types of proposals, the so-called sliding window proposal and the multiplier proposal. Then I will talk about two topological proposals, which are of course also very important. And just to keep in mind, we need to design proposals for which we either don't need to calculate a Hastings ratio or for which we can calculate it. And we also want to design proposals that have a good acceptance rate, so target is around 25%. And here, in practice, all sorts of tricks are being used to achieve a good acceptance rate. Like for instance, people have designed parsimony biased topological proposals that give you like a pre-scoring of possible topological moves, and then you just kind of draw from the good or the promising topological moves. You just kind of randomly draw one of the topological moves that are promising to achieve a good acceptance rate. Right, and so as I said before, the acceptance rate should be around 25%. So this is just an empirical observation. There's no theory behind it. But there is like one theoretical result that tells us that for sampling from a multivariate normal distribution, it has actually been formally shown that an acceptance rate of 23.4% is optimal. Okay, but let's look now at some proposals. So the first one, the simplest one that can be used for many parameters, not only for the branch lengths, is a so-called sliding window proposal. So here, this is kind of your branch length, like the allowed values for your branch length, and this thing here shown in red, this red line, represents the current parameter value. And then you use a sliding window of with delta, within which you're changing the value of the branch length. So basically you just randomly choose a point from here to set your new branch length value. So you propose a new value at random that lies within delta, and then basically you reevaluate your likelihood and calculate your prior ratios and the likelihood ratio and decide whether to accept or reject this new branch length. So some notes here: the Hastings ratio of this move is 1. The edge cases where we kind of end up going beyond, so if you have a value here and you end up going beyond the allowed limit, like the minimum branch length and the maximum branch length, so this can be handled by back projection. And an interesting additional thing here is that the window size delta can be tuned itself, so this is called auto-tuning, to obtain an acceptance rate of 1 over 4, like 25%. So this is a parameter of this proposal, and you can actually, as the MCMC chain generates more and more samples, you can try to optimize or tune this parameter delta to actually obtain a good acceptance rate. So, as I already said, so this proposal, the sliding window proposal, can not only be used for branch lengths, but also for other parameters like the alpha shape parameter of the gamma function of rate heterogeneity. Okay. Another proposal is for modifying branch lengths is the so-called node slider proposal. So here you don't change the value of one branch, but you change the values of two branches simultaneously. So step one, you just pick two contiguous branches at random, and then you multiply those two branches by the same random number. So you can see it here, if you go back and forth. In our example, you make them longer. And then in the third step, you propose a new branch ratio, B1 over B2 at random. So you change the proportion of those branches, of the one branch relative to the other. Right. And then you reevaluate the likelihood, so you calculate the prior ratio, the likelihood ratio, but also in this case the Hastings ratio, because the Hastings ratio of this move is actually not equal to 1. Okay, so those were like two examples of proposals that are being used for modifying branch lengths, and the other very important thing, of course, is that we need to move through tree space. So let's have a look at topological proposals. So one possible move here is that, well, you pick 3 contiguous branches in your tree, once again at random, that are shown in red here, and then those 3 contiguous branches actually define 2 subtrees, X and Y here. And then you just shrink or grow the selected 3-branch segment here by a random amount. So you just multiply each branch with the same fixed number, and then you either choose X, subtree X, or subtree Y. So we've chosen subtree Y in our example here, and prune it from the tree topology. And then you take this tree, subtree Y again, and insert it at a random position into the 3-branch segment again. And once you've done that, you're basically ready, and then you just kind of reevaluate. You evaluate the likelihood of this tree, then you calculate the prior ratio. So this is probably just 1 if you assume a uniform prior for the tree topologies. Then you calculate the likelihood ratio and the Hastings ratio. Okay. So here are the proposed tree. If we look at this again, like the this type of tree move, this is the original tree Ti, and this is the proposed tree Ti plus 1, or T star, to be consistent with our terminology. So in this new proposed tree T star, 3 branch lengths have changed, and 1 nearest neighbor interchange move was applied. So this is what happened here. And so now assume that this initial tree has a likelihood of minus 3,000, and the newly proposed tree has a likelihood of minus 2,900. So the question here is, will the proposed tree always be accepted? So maybe give you some time to think. Because the new tree, of course, we would expect it to be always accepted because it has like a better likelihood, which is like a log likelihood, which is closer to 0, which means that it is better. But you should think about the priors and the Hastings ratio, right? Because they also play a role, and they may actually lead us to reject this tree if the Hastings ratio or the prior ratio impact the overall ratio in such a way that it is below 1. So this can happen. So the point I want to make here is that, well, the fact that the likelihood improves does not always necessarily mean that the tree will automatically be accepted, because we also have the prior ratios in our equation and the Hastings ratios. Okay, now finally a little bit more complicated subject matter, our reversible jump Markov chain Monte Carlo procedures. So what do we do here? So now we know how to sample parameters, but what we do not know is how do we actually, can we use MCMC to actually also sample models? So here's an example. Consider all possible time-reversible nucleotide substitution models ranging from Duke's Cantor, which has 1 rate, to the general time-reversible model GTR, which has 6 rates. So what we will do is that we will denote the rate configurations of possible models by strings. So a string of 1, 1, 1, 1, 1, 1, 1 is the Duke's Cantor model. So it tells us that basically all 6 rates in our nucleotide substitution model are identical. And here, the GTR model means that, well, all rates are different. So for instance, if I wanted to have a model with 5 instead of 6 rates, I could write 1, 2, 3, 4, 5, and then maybe another 5 or 4 here. So maybe I will need to explain this further, but this is probably something that we can leave to the online discussion. Right. So one question here is, well, how many time-reversible DNA models are there? So this refers to the number, or this can be computed by considering the number of ways a set with n objects, or like 6 rates in our case, can be partitioned into disjoint non-empty sets. So for instance, consider the set ABC and the different ways that we can partition this set. So ABC can be partitioned as follows. So either A, B, and C are separate sets, or A is one set and BC is another set. So this would mean that those two nucleotide transitions, like the transition from, let's say, A to C and A to T have the same rate. That's what the grouping means here. So essentially A, B, and C, this would be our GTR model. We have like 3 distinct rates, and this would be our Duke's Cantor model, ABC, that we group all of them together and they all have like 1 rate. So the number of combinations for n, so 3 in our example, and 6 for DNA data, is given by the so-called Bell number. So if you're interested in the details about Bell numbers, you can see here. But here is a table of Bell numbers. You can see that for n equals 6, for our 6 rates, there are 203 distinct possible models of nucleotide substitutions. And those contain all the named models, like GTR, Duke's Cantor, HKY85, etc., etc. Okay. So, well, if we want to use MCMC to also integrate over all those possible models, what do we actually need? So, apart from our usual suspect parameters like tree topology, branch length, stationary frequencies, substitution rates, the alpha shape parameter, etc., we now also want to integrate over different models with a different number of free parameters. So what are the problems that we need to solve if we want to do that? So problem number 1 is that we need to design proposals for moving between different models, right? So now we're kind of, we're adding an additional dimension because we're jumping like from one model space to another model space. And problem number 2 is that those models actually have different numbers of free parameters, right? Duke's Cantor doesn't have any free parameter, and the GTR model has 5 free parameters because we need to optimize 5 rates or integrate over 5 rates. But the fact that those models have different number of free parameters means that we cannot directly compare likelihoods. So what we do here is that we use MCMC to not only sample model parameters, but also the models themselves. Okay, so here's problem number one. How do we approach that? How do we solve that? How do we do model proposals? Any ideas? How would you design a proposal that jumps from one model to the other? Okay, so here basically what we need to do is that we need to come up with two moves that either group rates together, rates from our substitution model, saying that those are now have the same rate, or we need to move a proposal that refines the grouping of the rate parameter. So, for instance, choose a set of substitution rates. So the split move will choose a set of substitution rates with more than one member at random. So this is basically a simple two-parameter model. So the first three rates of our substitution model are all identical, and then the last three rates of our substitution model are also identical. So here we would either, for the split move, we would either choose the series of ones or the series of twos. So assume that we've chosen the twos, and then we just randomly split it into two distinct sets of rates. So basically here we decided that the last rate, so this is probably the transition from G to T, will become a separate parameter, and now we have like a three-parameter model. So this allows us to propose a new model going from here to here, from a two-parameter model to a three-parameter substitution model. And then we have the merge move. So here we choose two substitution rate sets in our string representation at random. Let's say the two twos and the single three here, and we merge them into one substitution rate set. So here we now moved from a model with three parameters, from a nucleotide substitution model with three parameters, to a nucleotide substitution model model with two parameters. Okay. So here the question again is that we can also discuss at the online meeting as well. Is it clear to everyone what the respective rate matrix looks like? So given such a string, could you actually draw the respective rate matrix? So this is something to solve with pen and paper. Okay, and so problem number two is, well, we're sampling different models now. And that's what we're actually using reversible jump Markov chain Monte Carlo for, to jump between models or posterior probability distributions with different number of parameters, with different degrees of freedom. And so the model proposals we've designed in the previous slide are actually reversible jump moves. So if you just look at it here, it's easy to get from a model with two parameters back to a model with three parameters, then from here to a model with four parameters, and then back to a model with three parameters, etc. But evidently so, since the models we're jumping between have different degrees of freedom, we somehow need to modify our proposal ratio calculation to somehow punish the models that have more free parameters, because automatically, like if a likelihood model has more free parameters, the likelihood will improve. So we somehow need to correct for this. And in general terms, so the acceptance ratio now for this reversible jump Markov chain Monte Carlo method is calculated as follows. So our acceptance ratio is calculated at the likelihood ratio times the prior ratio times the proposal ratio, so if our move is not symmetric, so that's the Hastings correction, times the Jacobian. So the Jacobian, I will spare you the details, but the Jacobian transformation defines a linear map from r to the power of n, so vector space of real numbers with n components, to a vector space of the real numbers with m components at a certain point x, if this probability density function fx is differentiable at x. So I will spare you the details, but you can see here, if I start jumping around different models that have different degrees of freedom, it's evident that I need to somehow add an additional correction to the acceptance ratio calculation. Okay, so I will not provide further details, but if you're interested in them, you should have a look at the work by Peter Green who essentially made major contributions to the development of reversible jump Markov chain Monte Carlo methods. Okay, so here's a summary of reversible jump Markov chain Monte Carlo. So what we need to do is that we need to design moves or proposals that can jump back and forth between models of different dimensions, of different parameter counts, that have different free parameters. We need to extend the acceptance ratio calculation to account for jumps between different models. And then finally, well, how do I interpret the results? So the posterior probability of a specific model, so for instance, Duke's Cantor versus GTR, is calculated as the fraction of time, or like the fraction of samples generated, the reversible jump Markov chain visited or spent sampling within that model, right? So if 90% of the time my reversible jump Markov chain Monte Carlo method samples the GTR model, then the posterior probability for the GTR model is 90%. Okay, so that's the end of that lecture, and I'm sure there will be quite some things to discuss in the online discussion.